Okay, we're starting our new unit. This is the third rock from the sun unit, the geology unit. We're looking at chapter 14 in your textbook, and this is going to be slides 1 through 27. We're probably going to have 6 videos for this one. It's a really long PowerPoint, but there's tons and tons of pictures, so it should go pretty fast. Okay, so starting out, just to review the solar system with you guys, we know that the sun is the center. I hope you know the sun is the center of the solar system. The planets are divided up into the terrestrial planets and the Jovian planets. Terrestrial tend to be small, dense, thin atmosphere, rocky terrain. Those tend to be the ones closer to the sun, Mercury, Venus, Earth, and Mars, or they are the ones closer to the sun. So the first 4 are the terrestrial planets, and then the last 4 are the Jovian planets. And those are the bigger ones. They're much lighter, less dense. They're primarily a thicker atmosphere, a more gaseous atmosphere, as opposed to like the solid, denser terrestrial planets. And that's Jupiter, Saturn, Uranus, and Neptune. And remember, Pluto is no longer designated as a planet. Okay, so focusing on Earth, we're looking at 4 spheres, and this is kind of something that we've touched on a little bit to make sure, but to make sure you guys have it really clearly. The 4 spheres of the Earth that I'm going to refer to is the solid Earth, the hydrosphere, the atmosphere, and the biosphere, and that comprises, all 4 of those comprise the planet Earth. Okay, so formation of the Earth happened about a little over 4.5 billion years ago. Remember, this is formation of the Earth, and not the formation of the solar system. Formation of the solar system was a Big Bang theory. You know, everything kind of exploded outward and then kind of condensed and cooled off and settled down. But the formation of the Earth is the nebular hypothesis. So this happened, this nebular concept thing happened, they think, with all the planets and the sun all kind of at the same time, sometime after the Big Bang happened. And so what you had after the Big Bang was this really diffuse, thinly spread out stuff that was rotating around in space, formed into a disc-shaped body, which made our solar system, which then condensed into the sun and the planets. As everything cooled off, as the energy dissipated, it cooled and condensed more, and formed the planets that we have today. Okay, so distribution of elements in the Earth right now. There's over 100 elements in the Earth. However, 99% of the Earth is only composed of 8 elements. The rest are just very small amounts. So I would for sure make sure that you guys know these elements. It wouldn't be a bad idea to know the relative concentrations. So for example, iron, Fe, is the largest concentration in the Earth. And then oxygen, and then silicon, magnesium. So hopefully you guys are following along with me. Iron, oxygen, silicon, magnesium, nickel, sulfur, calcium, carbon. No, calcium, I was right the first time. Sorry. And then aluminum. Okay, so make sure that you guys are familiar with that. Okay, so looking at a diagram cutaway of the Earth, we see a couple different concepts that you guys should be familiar with. So the core of the Earth is the innermost part. The inside core is solid. The outside core is liquid. And then you have this mesosphere, and the mesosphere is kind of both. It's kind of weird. So you have this great big solid layer, and then you have this plasticky, like not really liquid but not really solid either, somewhere in between, kind of warm, kind of like warm Play-Doh or dough or something like that you can mess around and move, and that's the asthenosphere. And then the lithosphere is the rigid outer crust. Okay, so we see the crust is a very, very thin outside. The lithosphere is composed of the crust and part of the mantle, and the asthenosphere is just the plasticky part of the mantle. Okay, so you see where they're kind of overlapping their terms here. Okay, so the core is composed of iron and nickel, and the inner core is solid, the outer core is liquid. The mantle is homogeneous, whole way through is the same composition of that peridotite rock. Sorry, I can't talk today. And then the crust is heterogeneous. It's all kinds of rock types. It depends on where you are. Think about it. If we were right here, it wouldn't be the same rock and soil as if we were in the Appalachian Mountains. So it's very, very different. So the mechanical layers is the inner and outer core, the mesosphere, which is the lower mantle, the asthenosphere. So we're talking kind of the difference between the chemical layers and the mechanical layers. So if we go back to this slide, you see the chemical layers is what it's composed of, is the core, iron, mantle, iron and silicates, and then crust silicates. And then the physical is where we get into these extra layers with the lithosphere and the asthenosphere in it. So that's where you're kind of combining those two. So you have the inner and outer core, and then you have the mesosphere, which is the lower mantle. The asthenosphere is really important. That's the warm stuff. They're like the really weird plasticky feeling, flexible, movable. That's what ductile means, is able to manipulate. And it's beneath the lithosphere. The lithosphere is cold, is really brittle, is very strong. It's the uppermost crust and the top of the mantle that's also really strong and tough as well. Okay, same concept, different picture. I want to make sure that you guys are really clear on this. This one gives you distances to show you relatively, how big each one is. Notice how incredibly thin the crust is compared to everything else. And again, showing you at the surface, you see the mantle is composed of the asthenosphere and the mantle. The lithosphere is just the crust. You see how thin it is at the top. Okay, so all of this stuff that we've been talking about with the different biomes and the ecology and all that stuff kind of is dependent on the geologic cycle. So it probably would have made more sense to do this first. But Earth is a planet that is constantly being changed and moved around and shifted, and people tend to freak out about it, but it's really a very natural, normal process. Earthquakes, volcanic eruptions, plate tectonic movement, all of that stuff has been happening and will continue to happen for a normal, healthy planet. It will continually modify the Earth's surface and change stuff, which is good. All of the major processes are cyclic, which means they go in circles and continues. The movements that are happening, the earthquakes, the volcanoes, landslides, all that, tsunamis, all that stuff are very important to those cyclic movements. The reason that people freak out about it is we insist on building stuff, and when those cyclic movements or those big processes mess up what we build, then we get really upset and think it's unusual, but it's really not. Okay, so starting with the rock cycle. Rock cycle, 3 different types of rock: igneous, metamorphic, and sedimentary. Make sure you guys are comfortable with this. Okay, make sure that you understand who's going where and when. So you can start anywhere. This is a cyclic process. Starts, continues around and around in circles. Excuse me. Mine will start with hot magma coming up from inside the Earth. I then, as it cools off, as it hits the Earth's surface and cools off, it forms into igneous rock. So any rock that's created by magma, by melted down other stuff, is igneous rock. Now, igneous rock and metamorphic rock and sedimentary rock can all undergo this weathering and erosion, can all be broken down by the wind and the tides and impact with other rocks, earthquakes, whatever natural process breaks them down will turn them into sediment, will turn them into soil. And we'll look at soil a little bit later. Sedimentary rock is formed when that sediment is compacted and cemented, just kind of squished together really hard. But it's a mechanical process. The key here is that sedimentary rock is formed by a mechanical, lots and lots of stuff all together to turn it into rock. Metamorphic rock is kind of the same, but the mechanics is different. So this is a mechanical squish to turn it into sedimentary. Metamorphic rock is a chemical squish, chemical rearrangement. Heat and pressure changes the crystalline structure of the rock, and therefore it becomes a brand new mineral, brand new chemical formula, brand new mineral. So that's metamorphic rock. So you guys see the difference there. This is going to be the same chemical, the same chemical formula as the sediment. It's just squished, squished together physically, but the metamorphic rock is a different chemical signature. Okay, so I've probably said almost all of this. Igneous rock is when the magma cools off, crystallizes. You're going to have two different types. Extrusive is the surface, intrusive is inside the earth. Extrusive cools a whole lot faster than intrusive. Makes a lot of sense, right? If you're at the surface, you're away from the heat and the pressure that's inside the earth, so you're going to cool off a whole lot faster. Examples of that: granite, basalt, quartz, mica, feldspar, obsidian. So you have a lot of examples of igneous rock. So this is all cooled off magma. Sedimentary rock is where it's squished, compressed, and heated. Piling material over time. So it is a chemical change, but it's not a chemical into a new thing. It's a chemical from the sediment into the rock. Sandstone, shale, gypsum, limestone, and chalk are all examples of sedimentary rock. Remember, it's compressed and heated and chemically changed. Metamorphic is either of those, igneous or sedimentary, that are subjected to pressure and heat. Remember, this is when that pressure and heat is changing, taking the chemical signature that the metamorphic or that the igneous or the sedimentary rock started with and turning it into a different chemical structure. So if you take, I know I probably just confused you guys. Let me see if I can clarify. Let me see if we can go back. Okay. So if I take this, it's not a chemical change because you have the same chemicals in here, right? You're compacting them and squishing them. That's going to change the structure, the chemical structure. Not the chemical itself, but the chemical structure. Okay, so hopefully that makes a little bit more sense. And it's going to crystallize into sedimentary rock. Metamorphic rock, that heat and pressure actually changes that crystalline structure. So it's all the, they're both, I guess, technically a chemical change. That was inaccurate. But the metamorphic is a new crystalline structure, and the sedimentary is just a squished crystalline structure. Hopefully that clarifies a little bit better. Slate, marble, and quartzite are the metamorphic rocks. Okay, so this is a big concept. Plate tectonics is the big thing that we want to focus on right now. So the concept of plate tectonics, this is something that's been around. I didn't give you guys a history of it. If you're interested, you can definitely, I know all of you are going to run and look it up. In fact, why don't I offer some extra credit? We'll do, let's say, 20 points on a daily grade if you come and tell me when it was first proposed, when the plate tectonics theory was first proposed, and then who wrote the basis, later on, who wrote the basic theory that we use today. It's obviously been updated since then, but who was the guy that basically wrote the theory that we use today? Okay, so what that theory is that the lithosphere, remember that's the crust in the top of the mantle, is divided into about 13 big plates and a whole bunch of small plates. So it's not one solid circle globe. It's a whole bunch of pieces that are stuck together. From that, okay, so you can see that right here. So for example, you see the Pacific plate. You see where they've drawn the line to show you where they are. Notice that they pretty much encompass those mid-ocean ridges and around the continents. You see some of the smaller ones. A great big Antarctic plate. Okay, so you see, again, I would make sure that I pause here and I familiarize myself so I can look at a map anywhere and kind of know at least where the big plates are. The Pacific plate, the African plate, American, North and South American plate, Caribbean plate. Make sure you know where those big ones are because that's going to be important later on. Okay, so I forgot this was in here. I thought I had taken it out. Well, fine. Scratch your extra credit, guys. It's here. I'll come up with something else. Don't stress. This is a whole history. I'm going to let you read through it on your own. Make sure you know his name. This is the guy I was talking about, this Wegener. He developed the hypothesis. He first proposed in 1915. This is the guy that kind of wrote the basis of what we were. Of course, everybody made fun of him, but this is, you know, this is who came up with it. Okay, So the evidence for the continental drift, for the fact that those plates are moving, that's his big theory, was that not only is it composed of plates, but the plates are moving around, that the Earth is not the solid, immovable structure that we thought it was. The reason for that, for the continental drift, the fact that the continents are moving around, is a bunch of stuff. So we can look at mountain ranges, we can look at coastlines, rock sequences, similar fossils, animal similarities, and climates are all very similar. So if I go back to my map and I look at this, is it a coincidence that this right here fits this right here, and Australia fits right into here really well? Is it a coincidence that South America is shaped like this and Africa is shaped like this? Again, Africa here, North America here. Is that a coincidence? This is one of the big primary factors in continental drift. And then we see mountain ranges that continue really well all the way down through here. We see mountains here that would go into here. There are animals that, for example, have been found right here that are also found over here. How is that when there's a great big ocean in between them? A lot of evidence to support this. This is, obviously we have no way of proving it, so it's still technically a theory, but this is at this point an accepted theory that this is what's going on. There is a lot of proof to this theory. So it's developed, we took Wegener's idea, and then in the 1950s we developed it into the current plate tectonics theory. It's accepted at this point by almost all geologists. A whole bunch of explanations. It explains earthquakes, it explains volcanoes, fossil distributions, and orogenesis. All of this stuff is explained by the continental drift and the plate tectonics theory. Okay, so again, if you look at it, it fits together really well. You see the rocks. This is that rock. Remember I was saying that there were similar rock structures, all match up really well, especially up here once it all gets squished together. You see the animal patterns. How did this Mesosaurus get from one continent to the other? How did this Sinognathus, all these animals that are on these random places in different continents, how did that happen? Well, if they're all connected a long time ago, they would have been able to walk freely and therefore been on both places when the continents broke and drifted apart. So you see that animal fauna back up there. So what scientists have kind of pieced together in time is that we have this supercontinent 200 million years ago that has Laurasia, Pangaea, and Gondwanaland, and then we see the oceans as well. So we have this great big continent that was all stuck together. As we start to move apart after 60 million years, we see 140 million years ago where the continents have started to break apart. Antarctica and Australia, India have already broken apart. We see North America and Eurasia moving up. Africa and South America kind of moving northeast. And we see water starting to fill in between them. 135 million years ago, 65 million years ago, 135 million years of drift. We see them broken apart even more, starting to move around and spread out. And we see that water in between even more. And then today we see what currently the world looks like, with Antarctica all the way down, North America and Eurasia moving very far to the north. And I think, yes, that is where we're going to stop today.